Hi, my name is Brian Caffel, and welcome to the Resampled Inference Lecture as part of the Coursera Inference class, which is part of our data science specialization. So the Bootstrap is a tremendously important and useful tool for constructing confidence intervals and standard errors and basically performing inferences where it would otherwise be difficult. It was invented in 1979 by a famous statistician named Efron, who's in the Stanford Statistics Department, easily one of the top statisticians in history. And I would say the Bootstrap is one of the most important procedures that's been discovered in the history of statistics. And the reason being that it really liberated data analysts from having to do a lot of mathematics in order to perform inferences. So just as a simple example, if you wanted to do a confidence interval for the median, there are some kind of complicated asymptotics that you can appeal to, but it involves a lot of mathematics. On the other hand, you can just perform a bootstrap and it gives you a confidence interval for the median without having to do all of that work. So it, maybe dangerously so, but nonetheless, it liberated people from having to do a lot of complex mathematics to understand some distributional properties of statistics that they calculated. The phrase bootstrap comes from the name of the procedure bootstrap comes from the phrase pulling oneself up from their own bootstrap. That phrase, I initially thought it came from the Baron Munchausen character, which, by the way, if you haven't seen the Monty Python movie, you definitely should. I thought it came from that, but I've since read that it maybe even existed earlier than that. And the idea of pulling oneself up from one's own bootstrap is the idea of doing something that's physically impossible. And that's not a terribly appropriate name for what's going on in the statistical procedure, the bootstrap, because we can draw a direct line from the information that we're using to the inferences that we're making. So it's not at all like pulling oneself up from one's bootstrap. It's quite possible, and how it's working is pretty clear. So it's an important technique. It's very liberating. And I think it's also very much so in the spirit of data science. So consider this example. Imagine if we wanted to evaluate the behavior of the average of 50 die rolls. So our population distribution is this left-hand distribution, the equally weighted bars at the values 1 through 6. And there's a couple of ways we might go about doing that. One is we could just try and mathematically figure out what the distribution of the average of 50 die rolls is with no simulation, just doing the relevant algebraic calculations. Another way to do it would be to roll a die 50 times, get an average, and then repeat that process over and over and get lots of averages of 50 die rolls. But this is predicated on us knowing that the true population distribution is 1/6 at each number, right? But it does seem to be an easy way to do things, because it would be hard to sort of figure out exactly what's the probability of getting a 5.5, right? Instead, it's easier to just roll the dice 50 times, take the average, repeat that over and over again, and get a pretty good sense of it. Now, a lot of these things for the average we don't have to do because we know things about the distribution of the average. We know that it's centered at the population mean. We know that its variance is sigma squared over n. Several things like that. But I'm going to talk about it with respect to the average first, and then you'll see hopefully how this extends to other statistics other than the average. So let's consider a very similar problem. Imagine if you didn't know whether or not the die that was generating your data was fair. We didn't know that the probabilities it placed on 1, 2, 3, 4, 5, or 6. So what we have is one sample of size 50. So we only have one average, not a distribution of average, from whatever the die was that was generating the data. So here on the left-hand side, I'm showing you the histogram of the various occurrences 1, 2, 3, 4, 5, 6 for one sample realization that we drew from this population. Now I can't evaluate what's the behavior of averages of 50 die rolls from this population because I don't know what the population is. I don't know what die to roll from. to execute the simulation exercise. So what bootstrapping says is, well, why don't we do the next best thing? Why don't we sample from our empirical distribution, repeatedly sample collections of 50 die rolls, not from the true distribution, but from whatever our sample of size 50 estimates. So in this case, I would sample from these blue bars with the heights, with the probabilities related to the heights, and I would do that over and over again, and I would get averages, repeated averages of 50 draws from this distribution, and that would tell me about the distribution of averages, even though I only get to observe one real true average from the real population. And that's the process of bootstrapping. Mechanically, what we're doing is taking each observation, each 1, 2, 3, 4, 5, or 6 that we get, and throwing them into a bag, and then drawing out samples of size 50 where we're drawing with replacements. So the same the same data point might get taken out twice in this process. Sampling from that bag, samples of size 50, taking the average, and repeating that process over and over again. But the fundamental idea is to exactly replicate our simulation experiment that we would have done if we could roll the true population die with the observed distribution generated by the specific one realization of 50 die rolls that we got. Okay? And so that's the basic bootstrap principle. We use our data, our observed data, to construct an estimated population distribution. We simulate from that population distribution to figure out the distribution of a statistic that we're interested in. And that's the basic idea. So we'll go through some examples now with less contrived settings than this die roll example.